Well, thanks to everyone who's joined us today, and welcome to our webinar, A New Approach for High Salt Samples and TOC Analysis. This is the third webinar in a three-part series of webinars that I have presented this year. The first two webinars are available on the OI Analytical website, www.oico.com. So now, sit back, relax, and let's not worry about those high salt containing samples. In today's webinar, I will be covering the approach that OI Analytical employs for the determination of TOC on our Model 1080 TOC. I will touch on the importance of TOC, different TOC techniques, the effects of salt in TOC determination, and techniques that are used to mitigate the effects of salt. The importance of TOC as a water quality parameter cannot be understated. Generally speaking, when we think of contamination in water, that contamination is comprised of carbon-containing compounds. This is true for all applications. Ultra-pure water for microelectronics fabrication, boiler feed or process water, water for injection and clean-in-place validation in the pharmaceutical industry, drinking water, and wastewater. Total organic carbon is often used as a non-specific indicator of water quality. In the natural processes of our environment and the man-made processes of industry, the ubiquitous nature of carbon provides a screening tool to determine the status of water quality. TOC systems can determine contamination from naturally occurring compounds, man-made compounds, viruses, bacteria, or biological growth. TOC determination provides quick and easy indication of organic contamination. It can be used as a general screening tool and indicate if predetermined acceptance criteria are met for a wide variety of applications and processes. The United States Pharmacopoeia, European Pharmacopoeia, and Japanese Pharmacopoeia all mandate TOC analysis as a required test. In emerging markets, such as Southeast Asia and China, these practices are being adopted. For process control, a predetermined level of TOC has been defined, whether that be wastewater effluent from a chemical or petrochemical plant, or ultra-pure water for injection in the pharmaceutical industry. In those applications, TOC determination provides valuable insight into the proper function of the process. I will cover the oxidation techniques just very quickly that give name to the TOC analyzers that are available today. Today we have three primary methods for the determination of TOC in the laboratory: high temperature catalytic oxidation, heated persulfate with NDIR detection, and UV persulfate with either NDIR detection or conductivity or membrane conductivity detection. In this seminar, I'm going to concentrate on combustion TOC, as it is one of the most widely used techniques for the determination of TOC for samples with high salt content. However, if there's questions related to either heated persulfate or UV persulfate, then I'll try to answer those at the end of the seminar, along with any other questions. First, go over some of the characteristics of combustion TOC. I take these from Standard Method 5310B because it does offer pertinent information on the combustion TOC technique. While this is not a complete listing of all of the recommendations, these are the most salient points about this technique. In general, the combustion TOC technique is applicable when the TOC concentration is above 1 ppm. While the method does offer the choice of phosphoric and sulfuric acid, I contend that sulfuric should not be used, as this is a potential poison to precious metal catalysts. And if you'll also see down in the next to the last bullet point, there is guidance in 5310B about high temperature techniques and the accumulation of volatile residues in the analyzer. However, it does note that the 680 degree C technique minimizes the fusion of the dissolved salts, which is what we are talking about today. The combustion tube on the left represents a design that can be found in most combustion TOC systems on the market today. The combustion tube on the right is unique to the Model 1030C from OI Analytical. The principle of the technique is very straightforward. A small aliquota sample is injected onto a catalyst substrate in a combustion tube that is held at 680 to 950 degrees C. This temperature can be higher in some instruments that do not use catalysts. The advantage, as I've pointed out earlier, of using low temperature, 680 C, is that fusion of dissolved salts is minimized. So basically, we're going to have instruments that operate at 680 C, and these generally have an NDIR as the detector, platinum or some other precious metal catalyst, and the combustion tube itself, along with other packing materials, are comprised of quartz. So why quartz? The combustion tubes shown in the previous slide are constructed from fused quartz. Fused quartz is a glass consisting of silica in amorphous or non-crystalline form. The optical and thermal properties of fused quartz are superior to those of other types of glass due to its purity. Quartz glass is occasionally used in chemistry laboratories when standard borosilicate glass cannot withstand high temperatures or when high UV transmission is required. Quartz glass is always used in the construction of combustion tubes in combustion TOC instruments. Salt-containing samples are probably the most difficult samples for any TOC technique. This is particularly true for the combustion TOC technique. Aside from the deposition of salt on the catalyst and other packing material, salt leads to what is known as devitrification of the tube itself. Glass, any type of glass, is produced through the process of vitrification. A crystal, such as quartz, is transformed into an amorphous solid that we commonly refer to as glass. As one might expect, the reverse process of vitrification can occur under the appropriate conditions. For quartz glass, the process of devitrification occurs when quartz is exposed to salt-containing liquid at high temperatures, just like we have in a combustion TOC. The combination of heat and salt lead to devitrification. This process is accelerated if either the salt concentration or the temperature is increased. The picture on the left is a combustion tube from one of our modules that's used for TOC determination of solid samples. This picture was taken after the analyses of many beach sand samples that had relatively high salt content. The picture on the right is a close-up view of the center section where the sample is actually vaporized in the combustion tube. This is not just the deposition of salt on the surface of the combustion tube. Rather, notice the glassy surface of the quartz tube has actually started to crystallize. Eventually, this tube would lose its structure and collapse under its own weight. The exact same process can occur in a combustion TOC that's analyzing aqueous samples as well. So how do we deal with salt? There are a number of approaches that have been used to mitigate the effects of salt on the combustion system. Sulfuric acid. Now keep in mind, we're generally doing an NPOC technique in which we're going to use some form of acid to remove TIC prior to injection into the combustion tube. It is thought that potassium salts of sulfuric acid with higher melting point than sodium chloride have a positive effect on the lifetime of the combustion tube. Salt traps. Some schemes use a pad of quartz wool to absorb salt before it can reach the catalyst. Salt traps will ultimately clog and must be replaced. And once again, this does not prevent the possible devitrification of the combustion tube itself. Rinsing. Rinsing with water or acid will definitely have a positive effect on the combustion tube and catalyst. This is highly recommended as some, but not all, of the salt may be washed out of the combustion tube. In other schemes, ceramic tubes and valve surfaces are used. Ceramic tubes, while effective, can be rather expensive and will eventually require replacement. There are also special kits that use combustion tubes of a special geometry and packing scheme that have been used in some instances. And a very unique one, catalytic or catalyst regeneration. Some practitioners I know remove the catalyst, recondition with hydrochloric acid, dry, and return the catalyst to the combustion tube. While this may restore the catalyst, the devitrification of the combustion tube itself can still occur. One note about the use of sulfuric acid and catalyst poisoning. The conversion of carbon-containing compounds to carbon dioxide occurs on the surface of a precious metal catalyst in the presence of oxygen. If the active sites of the catalyst are not available, then no reaction occurs. Atoms, such as sulfur atoms, bond easily on the surface of a catalyst, thereby preventing the reaction. This is one of the reasons why I believe that sulfuric acid is not desirable in combustion TOC. So we see that there are challenges with the combustion TOC technique. And these are not found in other techniques by virtue of the fact that a combustion tube operating at high temperature is employed in the analysis. At some point, maintenance action of some form must be carried out on the combustion tube. This is generally confined to replacement of the catalyst. However, in some cases, complete replacement of the combustion tube may be required. As you recall, previous slides of looking at the combustion tube that was showing the effects of devitrification. Eventually, if we continued analyzing salt samples, that combustion tube will have to be replaced. This is particularly true for the analysis of salt-containing samples. The Model 1080 combustion TOC incorporates unique design features that help to mitigate the challenges that are faced in the determination of TOC and salt-containing samples. The two features that primarily address this issue are the Smart Slide Injector and the Catalyst Guard. In the pictures here, you can just barely see the catalyst guard tube at the top of our combustion tube, and this is looking down on top of the furnace and our cap and a smart slide injector. The Model 1080 combustion tube uses ramps in the slide to reduce friction while sliding across the sealing surfaces. So why is this important? If you see here, the ramps with this slider in the inject position are pressing down on the O-rings, which are just below this injection point. As this slide moves back and forth to load sample and inject sample, it lifts off the sealing surface, thereby reducing the friction of the slider across the valve surface. Now we're talking about salt samples. Some residue containing salt will be left behind, just a small amount, as this moves back and forth. However, that abrasive quality of salt in a liquid sample is eventually going to wear on not only the slider, the O-rings that seal it, but the body of the cap itself. So in this scheme, relieving that pressure minimizes the friction, thereby extending the life of the cap, the slider, and the O-rings that are sealing the tube. In our feasibility testing, using salt samples, the lifetime of the sealing O-ring was extended from 30 days to 15 months. And the anticipated lifetime of the slide is 18 to 24 months. Some additional features of this particular design: there's an off-the-shelf actuator that simplifies the design, reduces labor, increases reliability, and a quick disconnect linkage that easily detaches from the actuator and the cap for easier maintenance. In the catalyst guard design, we use a small sacrificial tube to protect the main tube and catalyst. So as the sample is injected, the sample first comes in contact with the guard tube, and we anticipate that the salt would be absorbed by the guard tube. And in this way, instead of the salt reacting with the main body of the tube, it will react with the guard tube and thereby take the brunt of the punishment. In our feasibility testing, this feature was tested with high salt and particulate samples. The guard tube was tested using a 3% sodium chloride solution. The Model 1080 ran for over 4,700 injections without failure of the main combustion tube or catalyst. As expected, the guard tube was not reusable. However, it could be replaced and the operation of the instrument continued. For those of you who might be familiar with the OI Model 1030C Combustion TOC and the combustion tube previously shown, that combustion tube clogged after 200 injections in the same conditions. This is a picture of the catalyst guard tube after the high salt test. It shows that the tube did its job in taking the brunt of the punishment from the salt-containing samples. Notice the devitrification of the quartz guard tube. This was expected. The salt in the sample contacts the guard tube before it reaches the combustion tube or the catalyst packing. When it's time for maintenance, and maintenance definitely will be required at some point, this tube can be removed, replaced with a new one, thereby extending the life of a more expensive full combustion tube. Now I just want to briefly discuss the results from a case study using high salt containing samples. We received samples some time back with unknown TOC concentration from one of our customers for analysis. Salt content was reported to be in the range of 33 to 30%. However, the exact salt content for each sample was not known prior to analysis. It was also thought that the TOC concentration would be in the range of 0 to 10 ppm. Therefore, the instrument was configured with typical settings for a low-range calibration. Typical settings for a 0 to 10 calibration curve can be shown on this chart. The samples were analyzed in MPOC mode. Sample and acid were added to the MPOC chamber and the TIC fraction sparged from the sample prior to TOC determination. One thing to note on our instrument, note the addition of the reaction time for the Model 1080. The Model 1080 uses a stop flow bypass injection scheme in which the sample is allowed to react in the combustion tube. I will not go into detail about that in this webinar. However, it was covered in some detail in the previous 2 webinars. Sparge time can be kept to 1 minute since the sparge flow rate is 300 milliliters per minute. So this sparges very quickly, very rapidly, very aggressively. Other items to note is that we typically run 3 replicates without outlier removal. As I said previously, it was anticipated that the TOC concentration was in the single-digit range. Therefore, the instrument was calibrated in this range. Most of the samples were in that range. However, 2 samples fell outside that range. Here we have the instrument IDs from the samples that we received. These are the results reported by the analyzer. And as you see, the 2, especially the last sample, was almost 10 times higher than the anticipated calibration range. Therefore, adjustments were made to the instrument to accommodate the unexpected high-range sample. The instrument was calibrated now in a range of 0 to 100 ppm, and the samples were re-analyzed under the exact same conditions. So when we make the adjustments to the new calibration range, typically the only thing we would have to change would be the sample volume. And this is typically true of the Combustion TOC technique, in which method volume, acid volume, sparge time are primarily the factors or the parameters that are required to change when you're doing different types of sample analysis. This is the calibration curve from the high-range calibration. All standards were matrix matched to the best of our ability with the anticipated salt concentration. So these standards were actually prepared in 3% sodium chloride solution. Each calibration point was analyzed in triplicate, again, with no outlier removal. And these are the results from the calibration curve shown in the previous slide. Again, it's noteworthy to point out that these are usually done on this instrument without outlier removal. The ability to run without additional replicates in order to achieve the results that we're looking for, especially in the application where we have high salt containing samples, reduces the wear and tear on the instrument. That is, these results are the results of 3 consecutive injections of each standard at each calibration point. And after we reran these samples, the results are shown here. These are the results from the analysis of unknown samples using the high-range calibration. For this one, check standards were inserted into the sequence at 10 ppm and 100 ppm. In almost all cases, the results in this calibration range were within 10% of the results of the low-range calibration results and the error in the measurement. The sample 40126 was nearly 100 ppm. Now that the method was optimized for this range, the blank at the end, just following this 100 ppm sample, was now well below what would be the reporting limit or the typical reporting limit for this type of sample analysis. In summary, samples with high salt loads generally are a problem for TOC determination. Salt can lead to devitrification of the quartz combustion tube and deposition of salt on the catalyst. Approaches taken for the mitigation of the effects of salt can be expensive or lead to negative effects on the catalyst. A simple, easy-to-use approach is employed by the Model 1080 TOC. The Model 1080 approach should result in decreased cost of ownership, downtime, and increase the mean time between maintenance activities. So, I've come to the point where I could entertain any questions. So Michelle, I suppose if we have questions for the audience, I would be glad to entertain those at this point.
Oh, we do, John, and we are getting some very good ones in. Our first question, Piper wants to know, could sulfuric acid or high sulfates concentration introduce interferences on the NDIR readings due to sulfur dioxide formation?
At very high concentrations, I believe it could. Now, our instrument does employ scrubbers in the flow path, although this is a copper scrubber that is typically used for halide removal, as well as one other scrubber in front of the detector that would probably help to mitigate that. But yes, I do believe it could, although the instrument does take into consideration with some other components in the flow path to help mitigate the effects, particularly of the halogens, to remove those from the sample stream before reaching the detector.
Also, could you please discuss the recovery rates at 680 degrees C for chemicals difficult to oxidize? For example, those that contain nitrogen.
Okay, well, generally speaking, many times in some of the applications we've done this on a case-by-case basis as far as determining recovery of hard to oxidize compounds. There's one nitrogen-containing compound that I know of, melamine, in which in a combustion TOC technique, we can generally obtain almost, and it is one of the most difficult nitrogen-containing compounds I know of to oxidize. We can obtain nearly 100% recovery of that particular compound, whereas that particular compound in, say, a heated persulfate method is very difficult to oxidize. Generally speaking, and this is another thing that 5310B also talks to in some of the guidance when using combustion TOC, that it would be a technique of choice for the more difficult or hard to oxidize compounds, whether that be carbon containing or nitrogen containing.
Oh, that's good. We have another question here. What range of salts do you call high salt samples?
Well, if we follow the guidance by some of the methods, anything that gets up above 0.5 ppm sometimes in some techniques is considered to start to be the point at which you might see difficulty. High salt for this, generally speaking, is going to be upwards, in the range that we saw there. But the brine samples, of course, are probably going to be the highest concentration of salt samples that we would probably have to contend with in a TOC analyzer. But just looking specifically at the guidance, particularly in 5310, it sets a limit much lower than even what we've shown here as to when salt, particularly in some methods, might start to become a problem for the analysis. And some of that is directed more toward the heated persulfate and the UV persulfate methods than the combustion TOC methods.
Oh, good. Also, wouldn't it be better to use a technique like heated persulfate for analysis of salt-containing samples?
Well, that's another one of those kind of all depends questions. As I've mentioned in previous webinars, particularly the second webinar where we did comparison of the various TOC techniques, not every TOC technique may be suited for every sample. Heated persulfate does have the advantage in that the residues which will be left in a combustion tube after salt and sample analysis will be washed out of the reaction chamber completely before the next sample is analyzed. So we can control that much better in terms of keeping the reaction chamber clean. However, it's well known that sodium chloride or chloride containing samples will react preferentially with sodium persulfate, and as such the persulfate is consumed before it has an opportunity to react with the carbon in the sample. Now there are approaches, and we've used these same approaches with our heated persulfate instruments, by increasing the concentration of the sodium persulfate. Typically we'll go from 10% to 20% and extend the reaction time, because we do have better control over that with our heated persulfate instrument, and allow that persulfate more time to react with the carbon in the sample. However, there is a downside to that one as well too, in that we're generating more water vapor, which we have to contend with downstream of the reaction chamber. So just depending on your preference primarily, I think you can obtain good results in both techniques. Again, the combustion TOC technique is known to have limitations when you start approaching lower limits, particularly around 1 ppm. And then in that instance with salt-containing samples, heated persulfate might be a better choice. It might depend, again, on the range of TOC that we're working with.
Okay, good. So another question here, is it applicable for water analysis with a salinity of about 400,000 ppm, or should we dilute the sample?
400,000 ppm?
Yes, sir. So
there's, I'm trying to do some quick math in my head. 1% is 10,000 parts per million, so we're looking at roughly 40%.
And that's I'm sorry, a clarification here. It's produced water?
Okay. Well, it's still water, whether we're going to have seawater or, although that might be a little bit different, but just dealing with the salt concentration itself, if I'm doing this off the top of my head, 40%. I think in a sample like that, I would first try to dilute that sample down into a range and give it a go just to see what kind of results you got. And then you might even dilute it and spike it just to see what kind of recoveries you're getting. But 40% is starting, even when if we consider brine, which some of the most concentrated brines are around 35%. That's really getting up there. I think if it were me, I would first try a dilution to see if I could optimize my instrument and reduce some of the wear and tear on it by diluting that sample.
Oh, that's good. Another question here: is there a best solution for dealing with salt in a combustion TOC?
My approach has always been whatever you can do to minimize the amount of liquid that you inject into the analyzer, the better off you're going to be. In our examples, we use our standard configuration settings when we analyze these samples. If we were going to try to do this again, we might even try to reduce that sample injection volume as much as possible. But in general, whether it's a salt-containing sample or particulate sample, any type of sample for that matter, when I'm working with a combustion system, I try to optimize around the least amount of sample that I can put in the instrument. Now, of course, our 1080 works a little bit differently than other TOC instruments on the market, in that the way it combusts the sample and these other features that are built into the instrument allows us to get away with some higher injection volumes. So sometimes we push that way. But in general, that's usually the key thing that I try to focus on when running a combustion TOC, and that's injection volume. Because we have to remember that whatever we put in, unless we can try to wash it out, it's staying. It's staying in the combustion tube.
Good point. So I think we have time for one more question. What steps would you have to take in order to mitigate the effects of salt with a technique like heated or UV persulfate?
Yeah, I kind of touched on that before. And the question in regard to the 400,000 ppm salt-containing sample, dilution is always a consideration. If you could dilute the samples, thereby decreasing the actual salt content, that's always going to be helpful. But depending on the range of TOC that's in the sample, and depending on what type of analyzer you're running, and in this case a combustion TOC, we already know if these are low level to start with, and we try to start pushing around 1 part per million, we're going to have some difficulty. But dilution is always a consideration. And then with heated and UV, again, to mitigate the effects of the reaction that persulfate is going to have with chloride in the sample, we start raising the persulfate concentration and extending the react time, which are probably the two biggest things that we can do with that instrument to mitigate the effects of salt.
Oh, wonderful. Well, thank you, John. That was a very useful presentation, and I think we learned a lot today. That that's all we have for today. And we thank you for joining us, and we look forward to seeing you again in future webinars. And we hope you all have a great day.
Thank you, everyone.